Welcome to Ask and Learn.
In this problem, we have a rod or a bar um, that's being supported by a couple of cables and also a ball joint. And we want to determine the tension in the cables and the reaction forces at the ball joint. So there's a rod extended out from the wall, and then there's a load acting on the end of it. So at the end, the free end where the load is acting, we have the external load has a magnitude of F1, which is given in the problem as 400 newtons, and it's in a direction in the YZ plane. So sine theta in the Y direction and minus cosine theta in the Z direction, and that is that's not our origin. That is 6 meters in the X direction away from the origin. A force acting on the on that end is the has a magnitude F2, so in one of the cables, and it's in a direction from point 1, this point here, to point 2, which I defined as where that cable is attached, and that would be that would be point C in the figure, or point B in the figure. And then in the other cable, we have a magnitude of the tension of the force is F3, and the direction is from 1 to 3, where point 3 is just 2 meters up from the origin, and that would correspond to point C in the book. We also have the force at the ball joint, so we have 3 components of force there, and that force is at the origin. So we have all of our, we can get our unit vectors now because we know the positions of 1 and 2 and 1 and 3, and so we can get these directions, and then we have all of our vectors for our forces and our positions, and we can sum, and this sum would go from, let's see here, 1 to 4. Sum all of these forces up and set them to 0, each component, and sum all of the moments up and set each component to 0. And again, some of these are going to be, one of these is going to be trivially satisfied, one of these equations. We actually only have, let's see here, we have 1, 2, 3, 4, 5 unknowns, and one of these again will be trivially satisfied and we won't need to worry about it. We can solve for our force components in terms of the applied load and then the angle at which it's applied. So it turns out that in the X direction at the ball joint we have 3F cosine theta, and the other components are actually 0. So we only have a component in the X direction, which is normal to the wall. The force in the one cable that goes from point A to B in the figure is 7/3 F1 times sine of theta, and the tension in the cable that goes from A to C in the figure is square root of 10/3 F1 times 3 cosine theta minus 2 sine theta. We're given values for all of these, so we can plug them in, and we can see that this component of the force at the ball joint is 1040 newtons. The tension in the one cable is 467 newtons, and in the other cable it's 674 newtons.